Hello and welcome back to FPV Reviews. My name is Spike and today we'll be discussing in depth how to determine whether your fixed-wing aircraft is suitable for a conversion from LiPo to lithium-ion cells. The lithium-ion technology has the potential to significantly increase your flight time due to superior gravimetric energy density, but it has some limitations and differences that we'll be covering, as well as how these differences relate to your specific airframe and power system. So let's get started. First, you'll need to know the maximum amp draw at full throttle while the aircraft is static. This is the first test in determining whether your plane is a good candidate for lithium-ion conversion, and if so, what kind of lithium-ion cells to choose from. Also, what kind of performance to expect. This is best measured with either a DC clamp-on amp meter or the telemetry you're using currently in the aircraft taken from the current sensor on board. You'll want to tie or hold down the airplane really well. Install the largest propeller you'll be using on the model and a LiPo in good condition that's been fully charged. The higher the C rating and the larger the capacity, the better. This makes sure that we know how much power the propulsion system is capable of demanding from the battery. It lets us make calculations to ensure that the new battery that we make is not overloaded. First, make sure you're clear of the props no matter what happens. Cycle the throttle briefly to make sure that the ESCs are calibrated. Not all ESCs require this. It'll depend on their firmware. If you're in doubt, just go ahead and go from idle to full throttle and back once, just to cycle them and make sure they're calibrated. Next, run up the motors to maximum RPM and record the reading from the amp meter or current sensor via telemetry. This should only require a few seconds of full throttle operation. What we're looking for here is the maximum amp draw that the motor prop combination is capable of drawing from the battery at the fully charged maximum voltage. We're going to use this data for the following determinations: cell chemistry suitability, minimum battery size, and optimal battery size for the greatest endurance. We'll also need to test the airframe's ability to carry additional weight and determine how it affects overall performance. Now, this is rather arbitrary, as there's not often a hard limit on weightlifting for a given aircraft, and increasing the weight usually results in undesirable flight characteristics or unacceptable landing distances long before reaching the point of diminishing returns in terms of weight of the battery and power required to keep the airplane in the air. The maximum acceptable weight also depends greatly on the operator and how comfortable they are maneuvering the aircraft at a given wing loading. Use a relatively aft CG for the tests that we'll be conducting next, one that allows good performance while still retaining acceptable pitch stability and good overall handling characteristics. This is going to ensure the best possible results for the next test. We'll be increasing the weight incrementally next, slowly adding weight to the aircraft, maintaining the precise CG or center of gravity that you determined earlier. Use relatively small increments and keep on adding that weight until the performance is noticeably diminished for the aircraft, watching the takeoff and landing distances grow. Pay some attention to these figures, and you might actually want to take notes on how much throttle or amps are required to maintain a safe minimum airspeed. At some point, there will typically be a much more noticeable effect on performance with incremental weight. For instance, a certain increment of weight increase, which was barely noticeable when the aircraft was lighter, say 100 grams, will have a noticeable and adverse effect at a certain higher gross weight as you start to add weight to the aircraft. You may also notice a particular bad tendency of the plane at a certain weight limit, or simply become uncomfortable with your ability to fly it or land it in a certain area. Any of these conditions mean that you should stop adding weight and evaluate the performance at a slightly lighter configuration when the aircraft still had quite a bit of extra weight, but still had good overall performance and handling characteristics. So go ahead and return the aircraft to that weight. Take it up again in manual mode taking it to a safe altitude, what we want to do here is thoroughly check the low speed handling characteristics. Now the aircraft will have a higher minimum stall speed than at the lighter configurations, but still should exhibit reasonable low speed performance and handling characteristics. Go ahead and stall the aircraft and observe how it responds. Some aircraft have a tendency to tip stall at higher wing loadings, and some not so much. It's important to understand exactly what these characteristics are. Just be sure that you have extra altitude to recover at these increased weights. Be very cautious doing this test with aircraft that have very thin wings, low coefficients of lift, and large control surfaces, as it's possible for them to stall again while trying to recover from the initial stall. What this results in is a cascading series of stalls all the way to the ground. Also, a word of warning with flying wings is adjusting their center of gravity further back beyond a certain point, although greatly enhancing their efficiency and their ability to lift weight, will likely cause them to be unstable at higher angles of attack, also have poor stall spin characteristics, and be much less stable in yaw. So with these poor stall spin characteristics, it can actually be impossible at some point to recover the aircraft, and they can spin right into the ground. So, but if you have a plane with a fairly thick airfoil, relatively thick, and reasonably sized control surfaces, should be fine. That's more what we're looking for here. So now that we know how much weight the aircraft can safely carry in terms of added weight, we found that ideal amount of weight for the aircraft, we can go ahead and determine what kind of payload we'll be using and how much that weighs. So doing just a little math here, we want to add the weight of the existing Lipo that we used for the test and add that weight to the amount of weight that we added during the test, and then you want to subtract the payload weight. And what that gives you is the weight of the new battery that we're going to be putting in the airplane, or at least the maximum possible weight of the battery. So now that we have that data, we can do some basic calculations. Now, don't be intimidating on that, as they're actually quite simple. Ideally, we would use the highest capacity cells that we can find available. For instance, such as the NCR 18650GA from Sanyo. So let's see if they can be used in your aircraft. Is there an ideal solution at this time in terms of gravimetric energy density? So let's say our hypothetical aircraft draws a maximum of 40 amps at 3S or 11.1 volts at full throttle during the previous test. So each cell can output a maximum, absolute maximum, of 10 amps each continuous under ideal circumstances according to the manufacturer. So we'll need at least 4 cells in parallel in each group. Now we highly recommend that you give at least a 20% margin in amperage for the battery pack. So let's do the calculations for 5 cells in each group and consider that to be the absolute minimum battery size for that aircraft. So 5 cells per group in parallel, 3 groups in series. That's 15 cells, and each cell weighs just under 50 grams. But we'll call it 50, as there are at least a couple of grams per cell in solder and wiring to make a usable battery pack. So 15 times 50 is 750 grams. If your hypothetical aircraft can carry at least that weight, then it should be practical to use a high-capacity lithium-ion pack. If not, then you may want to consider a different lithium-ion cell type, such as the LG-H2, which can deliver double the amperage at 20 amps per cell. So go ahead and recalculate using that figure. Just be aware that the capacity of such higher amp cells is less. In the case of the LG-H2, it's 3,000 milliamp hours per cell, compared to the GA cells, 3,500. The gravimetric energy density will be a bit less, but will likely still be better than LiPos. Now, if the calcs worked fine for the GA cells, and the weight calculation for the smallest possible pack is less than the maximum battery weight that we determined earlier, then we're going to recalculate ever-increasing cell counts until we reach the maximum battery weight the aircraft can carry safely. First, let's assume that the hypothetical aircraft can carry 1,300 grams of battery weight. Let's add one cell at a time to each group and see what battery configurations are possible. So with 6 cells per group, that's 18 cells, so 900 grams. So that's one possible configuration. 21 cells would weigh 1,050 grams, another possible. 24 cells would weigh 1,200 grams. 27 cells would weigh 1,350 grams. So that's just slightly over the 1,300 grams that we determined, so we would return to that 24 cell configuration. So what's the right configuration of all these possible battery sizes? Well, let's determine what factors will drive our decision as to which pack of those possible configurations that we actually want to use. We're going to look next at voltage sag and watt hours. So the higher the discharge rate that you require from the battery, the less capacity in amp hours you'll be able to get from the pack. But that's only part of the story. The specific voltage level that the cells are able to hold while delivering that amp output will have a further effect on the total watt hours the pack can deliver. The watt hours actually is an effective way to measure the battery output. These factors are present in all lithium batteries, but are much more pronounced in low discharge rate batteries in general, due to increased voltage sag for a given load and capacity, all things being the same. The same factors are even more pronounced in lithium-ion chemistry cells because they have a different voltage range than LiPos. Both have a fully charged voltage of 4.2 volts per cell, whereas the LiPos almost completely drained at 3 volts and will most likely be damaged if taken any lower, whereas the lithium-ion cells can safely and repeatedly be discharged down to 2.5 volts per cell, and indeed must be to get the total percentage, whatever percent you're drawing from both packs, that's equivalent to the LiPo. So this is difficult to calculate as the voltage sag is far from constant over the course of most flights. It's likely to be very different, the voltage sag, when the battery is fully charged, when the airplane's during a takeoff, a climb, cruise, loiter, or glide. It can only really be calculated by plotting a complete discharge curve for the flight profile in consideration of the area in the lower side of the curved line. This factor is often one ignored by people testing lithium-ion cells in comparison with LiPos under less than ideal discharge rates. They're often left wondering whether the cell manufacturer's lying regards the specs, or if they've purchased fake cells that have been relabeled by an unscrupulous third party. Just looking at the milliamp hours is not sufficient, and it will not necessarily correspond with flight time compared to LiPos at higher discharge rates and at higher average voltages. One thing we can be sure of is that using the largest pack possible ensures a lower discharge rate for each cell and enables us to get the most real-world capacity from the lithium-ion technology. As with many performance enhancements, leveraging multiple factors will give us a compounding result that is positive and more closely matches the manufacturer's specs for the cells. For this reason, combining an endurance-optimized airframe with the largest lithium-ion pack possible can achieve the most spectacular results, whereas using the same cells in a sport aircraft will likely have more disappointing results, and we may be left wondering why there's such a large difference between the specs that we're seeing and the ones from the manufacturer. Another into account when attempting to calculate specific performance. In most climates, simply ventilating the cells with air flowing by is more than sufficient to ensure adequate cooling. In some colder climates, it may be necessary to limit the amount of airflow, preheat the battery to above room temperature, and in some extreme cases use a thermal insulator to retain some of the heat produced during discharge. If this method is used, it should be done carefully so as not to trap excess heat in some of the cells. It will be necessary at some point in the future to develop more sophisticated heating and cooling systems for these type of applications where extreme ambient air temperatures prohibit passive air cooling, such as is done with some electric automobiles. If the temperature control system is kept lightweight and efficient, its added weight should be able to easily offset during operations in extreme environments the increased battery performance by the increased battery performance, because the cells are now able to operate at the proper temperature at all times. It will also help extend the useful cycle life of the cells. These methods of insulating, heating, and cooling batteries are commonly used on spacecraft today, but it should be more easily achieved within the Earth's atmosphere due to the possibility of using convective cooling and not just radiant cooling. This applies to higher altitude flights as well, as the ambient air temperature at altitude is often much colder than at ground level. You can use the following approximation for purposes of flight planning using a passively air-cooled pack. So, for every 1,000 meters of altitude, subtract 9.8 degrees centigrade from the ambient temperature. Or in American, it's about 3.3 degrees Fahrenheit for every 1,000 feet increase in elevation. Considering the temperature gradient is also useful to make sure that your high altitude flight does not take your airplane into known icing conditions, at least until we develop de-icing systems for small UAVs. So in summary, in order to make the best use of lithium-ion cell technology in aircraft, make sure the power system is adequate to provide enough thrust to climb near the end of flight when batteries are nearly depleted, and carry the largest battery that is practical for the aircraft. Use the cell type with the greatest gravimetric energy density available, which also gives you a safe margin of amps output at full throttle, keeping battery temperature as close to ideal as possible throughout the flight. The spec listed on the GA cell datasheet shows the optimal discharge temperature to be 25 degrees centigrade or 77 degrees Fahrenheit, and that carries over for many other types of lithium-ion cells too. Also, pick the aircraft that can carry the most weight while using the least amount of power to stay airborne. This aircraft type is called a long-endurance platform or long-endurance UAV. They usually fall into three categories depending on size, performance, and equipment. LALE, low altitude long endurance, MALE, medium altitude long endurance, and HALE, high altitude long endurance. There's also a fourth category called perpetual aircraft, also referred to as atmospheric satellites, which commonly can use this type of battery technology. That last category is usually powered by solar, but could possibly ride mountain wave lift to stay aloft for extremely long periods of time. The potential for both of these has been well demonstrated recently by Solar Impulse 2's around the world flight, and the records being set currently by the Perlan 2 glider. These type of methods are also known as in situ resource utilization. Although the power may come from solar, or in the case of the electric powered aircraft, the energy storage is stored with very similar to this lithium-ion batteries, and also stored using the altitude of the aircraft by climbing during the daytime in sunlight hours and letting the airplane descend slowly giving up its kinetic energy to trade for forward motion and flight duration during the night. So we hope that you found this information useful from a practical standpoint and inspirational as well for what's possible in the future. Don't forget to smash that like button, hit the bell icon to get notifications. Make sure you subscribe to our channel so you don't miss the next episode. Also, check out our website at the link below for more info about our innovative and exciting projects. Have a good one.